Full screen. Full screen, okay. So, why it is not reacting? We went left. Okay. So look at the flow. What happens there? On the left plot, you see when once we fix the transition, the leading edge, we initiate the transition of turbulent boundary layer, and because of that, it grows and it influences the flow, so it gets. And because, as we said, when we have a boundary layer and we want, so there is a practically displacement of the body in the thickness of displacement thickness. So the actual body, as felt by the flow, is thicker, so it accelerates more the flow, upper flow, and then because of that you get shock wave ahead of what is going in full scale. So by initiating the transition, you are promoting the location of the shock wave, and then you get this phenomenon that we saw in the earlier, on this earlier view graph slide.
But does it
Hello?
happen because of grid application? Does it happen that the speed becomes that much so that
once when you the boundary layer becomes turbulent, the thickness of the boundary layer is bigger.
yes.
It's bigger. Once it's bigger, displacement thickness is bigger, larger.
Right.
And the meaning of displacement thickness is that your boundary layer actually swallows one of the volume of mass it should transfer. So the layers above had to accelerate, speeding up.
Yes.
Once they're speeding up, you get your Mach number 1 earlier. It accelerates, and you get Mach number 1, Mach number, shockwave.
It is already a high-speed flow.
Yes.
It is already high-speed flow.
Yeah, it is critical Mach number. It's critical Mach number that you get shockwave on the full scale, but on the full scale you get it down, and the wind tunnels, because of you promote it, you prepone it. So you get false situation. Oh, this is working? Yeah, this is working. Thanks. That's a false situation. Okay, the other one is describing what I told you.
And how about moment, sir? Moment.
Tell me.
Moment.
The moment affected by that, you just integrate the pressure here.
Different pressure. Due to shock wave at different location, moment will be different due to pressure different
Yeah,
distribution.
yes.
And how to take care of that?
You cannot. I mean, you just have to make your wind tunnel different. You cannot correct the results. That's what the flow has to tell you. That's what the flow's giving you. Any correction you make, it's not a direct action because it's not the real flow. You get different flow. So you start with something wrong. You have to correct your flow. You have to find a way to simulate the real Reynolds number. And this is the cryogenic.
Which is conservative, sir.
What do you mean? How much?
Actually
Look,
is placing it downward.
when
Whereas
you
this
are-
one is there in the center.
When you are planning, designing your control loops, control equipments, you don't want to be conservative. You want to be exact. You want to be precise. You cannot take this in account. You have to be precise. So we must find the way to get accurate, to get something similar to what you have on the left side. So this is concluding. Oh, not yet. This was in this was in transonic, and this phenomena happens in the shuttle. Mach number 23, hypersonic, hypersonic. It's a very known phenomenon where they almost missed the re-entry because of that, because they didn't have enough elevation. I mean, it was not reacting according to expectation because of differences between real gas and the perfect gas. The wind tunnels, usually the cold wind tunnels, are working as perfect gas. And what I was discussing earlier, the interaction and the complicated regions are different when you're talking about real gas. The bore shocks are sitting differently, so the moments are different. And it came out in practice. They had to push something like 5 degrees more what they had to in order to get into right entry trajectory. And I don't want to tell you what happened if they couldn't. If they don't, the entry corridor is only 3 degrees. The entry corridor of the shuttle to get in back to the atmosphere, it's 3 degrees. They must get into that corridor. Otherwise, if they get higher, they can go somewhere else. I don't know where to. They don't know. And if you go lower, they get just impact. They just accelerated to ground. So this was really. Did you see Apollo 13 movie? Apollo 13? That's a great movie. When I was giving this course, Hypersonic, I sent everybody to see that movie because it shows what technical efforts they are meeting there, and they were meeting there in order to stay alive. So these kinds of errors could come when you are not fully simulating the flow. So this was the second presentation. The last for today, I'll put it here. Okay. Now we'll survey different type of wind tunnels and what their capabilities and what their activities on top view, on briefing. But so we'll repeat some things that we have done so far, and we give a promo to what we are going to do later on. So this is arbitrary division of the range of wind tunnels. Subsonic below compressibility, 0.3. Transonic, we say between 0.3 up to something beyond Mach 1. Everybody can adjust it to his own wind tunnel. In the tunnel I was working, the transonic test section could run up to 1.8, but anywhere else it can be something else. Supersonic considered beyond that and below Mach 5. Mach 5 is relatively acceptable as the limit for hypersonic. Again, it's an arbitrary number. If somebody comes with 4.9, nothing happens. If somebody comes, but one of the definitions of hypersonic is the Mach number that you have to hit the flow in order not to get liquid when you accelerate or expand to high Mach, to Mach 5. The moment you have to hit your flow, that's a Mach number, that's hypersonic. That's one of the definitions. So it's roughly around 5. You can run Mach 5 without hitting your stagnation conditions. You can run with the standard conditions and expand to Mach 5. And generally, you shouldn't liquefy your air. But beyond that, you must heat your flow. You know that once it expands, it won't liquefy. So generally we'll talk about two types of wind tunnels. One is open circuit and one is closed circuit. On all the ranges you can find closed circuit and open circuit. As the name is, the open one, the air is sucked on one side and blows to the atmosphere, and in the closed circuit it just circulates. And you will find it mainly in the low speed, the closed circuit, but also in other ranges. And within those two types of wind tunnels, there are also two types. One is the open jet, open test section, and one is the closed jet, closed test section. Now, for each one of them, you'll find, as always, some advantages and disadvantages. So, generally speaking, the open circuit will be cheaper, less cost, because the shell is shorter. You have only one leg out of 4, so it should be less cost-wise. And another advantage, technical one, is if you want to make visualizations to inject smoke or fog, you want it to be exhausted to outside. So it's a big mistake if you make an open loop and you put it in your big hole, then all the hole will be full of smoke. You better find a place where you can connect it to the wall and send it out of the building. That's a big advantage. So once you think of open loop, you better think of where to put it, find a window in the place so you can blow the air outside. Then you get a big advantage of what you're doing. The disadvantage is that it'll have disturbances. It'll be disturbed by the income. If it's not a quiet environment, I know one of the wind tunnels in Bangalore, the entrance is somewhere outside, and every wind can affect, because 1 meter per second, 4 meters per second wind, when it's sucked, you get one component vertical, perpendicular to the mainstream. It's bad. So you would prefer to have your air to be sucked from quiet environment. So if it's within the hole, you just make sure nobody is disturbing this. You just close the doors and make sure you have some ventilating so the air will return. That's the best thing, to suck it from the hole. Just don't let anybody sit next to the entrance there, so it won't suck all his papers and I don't know what. And it needs more energy to run, naturally, because on the closed loop, you just have to maintain and to take care of the energy loss according to friction. Once you get the speed, it's like keeping the momentum. It's like a car. You drive a car, and all the force and the power you invest is only the friction and the resistance. It's not nothing else. It's nothing else. Where in the open loop, you have to accelerate stagnant flow to the velocity in the test section. So this is a net energy that you have to invest continuously. In addition to this, you also have to invest on the drag friction that you have in your open loop. So it's in addition. So you have two contributions to the power that you need. One is the acceleration of air. Second is the energy loss according to friction or whatever you have there. The advantages of a closed circuit are whatever is disadvantage there. Quality of flow is controllable. More controllable. You are not affected what happens outside. It's within. and whatever you do, that's what you get. We said less energy required, and that's all. Disadvantage, construction is, as we said, more expensive. And when you make a flow visualization, you'll have to stop sometime because it will be congested and you will not see anything. Everything will be smoggy. And also, all the alarms will start and operate in the building because you have some material that disturb the sensors. And it happened, I'm telling you. In the wind tunnel in Tel Aviv, we were doing this. I was insisting to have a closed circuit one. And we started to make some visualizations, and we didn't care of the alarm sensors. And at the point, the whole building was crazy. All the building was in alarm. So this is an disadvantage. Then you have, of course, we had the doors to open and ventilate the tunnel level. To start with, you have to ventilate it after some time. Otherwise, you don't see anything. And also, you may need cooling. Once the air is circulating, energy is absorbed by the flow, and the temperature is rising slowly. So you may need to cool it. Depends on the velocity and the heat flux from the tunnel. The message, the real message, the main message from this discussion is, when you plan to have your wind tunnel, try to put the leg of the fan in the closed circuit. Try to put the leg of the fan outside your laboratory, so the noise will be outside, and you'll gain space. Because if the whole layout is within the building, you lose space unnecessarily. I was lucky in Tel Aviv when the college wanted they wanted the wind tunnel, and I said, this time I wanted closed loop. And I was supported by the president, who had to be one of my instructors on my studies. He became president. I told him, we'll make a closed loop. You support. And he supported. But then they say, oh, you'll close all the lab. No space. There was no enough space. Imagine this kind of room. And it was full of fluid mechanics laboratory. And then somebody comes and say, okay, now will be a wind tunnel here, 10 meters long, 5 meters width layout. That's it, finished with the lab. I said, wait. I saw that there is a patio there, unused, outside that room. So all the 3 legs were outside. Only the testing leg was inside, so we saved a lot of place. So if you have this thing, you save a lot. And for the open loop, as I said, try to exhaust the air outside. So the fan will be also located outside because it's always suction. And also the fog and smoke, whatever you do, will just straight go out. Just be careful who is standing there outside. The guys who are smoking outside or whatever, they won't be scared. One of my guys lost his specs when we ran the full speed, and he was going next to it, and he lost his specs there. So that's it. Now for the test section, open test section, for the open circuit, you need to close. Because if you don't close the area of the test section, it will entrain flow. Instead of entraining it from the nozzle, it will entrain it from the test section. It's wrong. The flow will be bad. So you have to close this test section anyway. Not on the walls, but somewhere you have to close it. Otherwise, you'll have this wrong flow. And
But then there would be net entrainment as such. You would have circulation in that because the mass is anyway conserved in the.
if
This is open jet type or closed loop?
if open loop for the open circuit. For the open circuit, you have a suction fan downstream. It sucks air, right? and you want the whole flow to come from the nozzle. But if your open test section is open, it will suck through the test section. So you have to close that place. Anyway, you have to put the chamber that will not let air be sucked from there. You have to maintain the pressure there, so the air will not be sucked from there.
And flow will also be slow as well. I mean, as
Yeah.
well as from side it will be coming. So from side.
Anyway, it will be noisy. The test section will not. It'll lose its shape. If you have entrainment, it's not anymore test section.
But if it's a blower type of tunnel, then this from
Yeah, blower. It may also entrain. May also entrain flow. Also, it may also entrain. Yeah. And when you have external balance, you must have wall anyway to you need one boundary for the external balance. For the closed loop, it's less problematic. And most common is for the closed test section is the closed loop. Anyway, I hate the feeling that it will be noisy. By all means, the open loop will be noisier. Anyway, because you have this shear layer there, and the shear layer grows like 1 to 10, 1/10 width. So it will be noisy. I would never go, whenever I can, I would never go for that, unless you are making a car, ground transportation elements which are not sensitive to the quality of flow there. You are not expecting zero turbulence or whatever. As long as you have good flow there. You see, I show you Mercedes? Did you see Mercedes wind tunnel? No, we didn't see? All these wind tunnels are very short. You have these fans, and contraction is very close, and it looks very funny, those wind tunnels. But they make their job. We missed that view. If I want to show you, just a second. They have a nice selling video. It's not so technical, but it's selling. Just a second. No, why it came here? I don't know. It's not the one I wanted. Let me see. That's why we didn't see it. This one. Wake up, wake up. It's a nice video. Very professional, commercial. What are these? Streamlines, strict lines, or path lines? What are these? Strict lines. Strict lines. Only for that you can be sure. If the flow is not steady, it's not only strict lines, because they're all coming from the same source. But okay, you can say streamline. If you ask the guys, they'll tell you, okay, the streamline. That's the streamline. Tell me. Test section and then the open the wall there. This is the inlet, the new inlet test section, and then they open this this wall. So it's an open loop with the fan here. So it was modified. That's the way they got this biggest one in the world. See how small the guys look like. You get a feeling of what size is this. Car testing, we have just seen that one, the Mercedes-Benz. This is the nicest wind tunnel I've seen in my life. It's Pininfarina in Italy. They know, they have very delicate taste, the Italians. And the cars are very nice. And even this facility, if you measure the flow there, the quality would be very bad. Because you don't have any, you have the fan, and then immediately then you have the nozzle, and this is like a showroom. It's not like a wind tunnel. But they have the stream, and they run, and they develop nice cars. And what we say, used to say in aerodynamic that nice configuration is a nice airplane. If your airplane is ugly, probably you won't fly good. So the same with the cars. If they are nice, probably they are effective and they are cost a lot. So this is Pininfarina in Italy, and you saw already that D&W in Holland. Another type of wind tunnels are the low turbulence. If you want to have some research, this is mainly for research on flow, stability. Wind boundary layers, you want to check what are the parameters and of transition and so forth. You need to have a very quiet wind tunnel. And when you talk about low turbulence, we're talking about 1/100th of percent turbulence level. So this is of the NBS, National Bureau of Standards. I almost got a hand on this, hold on this. The main operator or researcher in that one had good relations with us, and it didn't work out finally, but I wish we could. I don't know if you deal with boundary layer stabilities and this, and you look back at NASA, there was one fellow by the name of Klebanov, Skramsted, all kind of names, European names, people which immigrated from Europe those days, wartime, and came to work in NASA and US, and good people. So they were working on stability, and this is kind of wind tunnel they were creating.
What do you do to reduce the turbulence level in this kind of?
We'll do it in the course. You'll know what to do. You'll know what to do. Tomorrow we'll design a low-speed wind tunnel, and the last day we'll make a session hands-on. You'll have to calculate and build on your own wind tunnel. Yes.
Previous slide, can you explain the last thing? Is expected to have
In order to work in such projects, in such programs, basic research of stability, you need to have it this level of turbulence. Level of turbulence. Otherwise, your flow will disturb, and you will not have laminar flow enough. Reynolds number is it's a necessary condition, but it's not sufficient. Like you learn in mathematics, it's like in pipe. You know the Reynolds experiment with the pipe. What's the transition number for pipes? 2300. 2300. Okay, this is transition number for pipe flow, but it's necessary, but it's not sufficient. You can run in a pipe laminar up to 100,000 Reynolds if the flow is very quiet, and you need disturbances to blow up turbulence. Like you freeze your bottle of water in the freezer, and unless you take it and shake it, sometimes it's still water, even it's minus 20. You need some disturbance to motivate the flow to change position. Okay, it's like stability. Stability, when you know stability, when it is a valley, it's very stable. When it's a mountain, it's very unstable. But you need something to push it, just start it. But if nothing happens, it may stand there on top of the hill. So the same with the transition in boundary layer. If you want to find out what are the frequencies and so forth to disturbing the flow, you want it to be laminar as far as you can. And for that, you need the free stream to be quiet. And the typical figures are hundredths of a percent, not more than that. Though in regular wind tunnels, we are running with quarter of percent, 0.2%, something like that. We can run. Nothing will happen. Another type of wind tunnels, it's not a type of wind tunnel as it is a type of testing. The regular standard procedure is to calculate the forces and moments. And from there, you can exert the derivatives, first derivatives, static derivatives, to get coefficients for your equations for simulation. But once you need dynamic coefficients, you need some dynamic facilities to exert your dynamic coefficients. So if you need pitch moment, dumping, you have something with flexible mounting, and you check what is your dumping coefficient for any certain configuration. And this one is rotary. When you need rotary coefficients derivative according to roll, you need rotary balance. And if you want to see what really happens, you use this tunnel. Which during the year you go there and you parachute, but the development work is what you see here. Yeah. So here you see a vertical tunnel. This type of tunnels are used for recovery from spinning. When an aircraft is stalling, you have to see that it recovers. This is one of the conditions that aircraft will be certified. Because if it spins, you have to find a way how to get out of it. And you can test it in such kind of wind tunnel. In this case, they were testing the capsule, the Apollo capsule, to see what are the conditions that it will be stable and what conditions they will not be stable. You know, the entries with the wide base. They'll get back to this, by the way, to this configuration. It's safer than the shuttle. So this is a vertical blow, and they throw the model and they see how it is reacting. Of course, it has to be simulated in terms of mass, moment of inertia, to simulate scale down to the model. Once it is dynamic testing, you have to simulate your dynamic features of the model. Usually you just simulate the shape of the model because you need to know the aerodynamic coefficients. But if you want some dynamic response from the model, if it's flatter, you have to you have to simulate your stiffness of the model and the mass distribution. You have to simulate it fully. And when you are drop testing, you have to simulate the mass and the moment of inertia. Okay, we saw this. These tunnels are not clean. They are long. They have long test section because they want to develop a huge boundary layer, as in life. I mean, atmospheric boundary layer. They are very tall. They are very high. So they are the test sections of this kind of environmental, meteorological, environmental. This is Colorado State University. They are very long. The contraction ratio is very low. It's 1:4, something like that. And they are not so valuable for aerodynamic. I wouldn't recommend to take any aerodynamic testing there. So we covered on the top survey the low speed, and let's see what we can find. High speed generally, it's divided again to open circuit, and within open circuit we have blowdown and in-draft. Blowdown is blowing the air to the atmosphere, and in-draft is blowing to vacuum chambers, vacuum vessels, storage. And closed circuit is closed circuit, continuous. You find it less in the hypersonic, if at all. You can find high-speed wind tunnel, high-speed wind tunnels, closed circuit wind tunnels, continuous, but these days rarely. So the closed circuit, it will have a closed shell with a drive motor and a fan and compressor to press the shell, and it will consume hell of energy. You need a power station next to your place for this kind of wind tunnels. If it has some reasonable size, this kind of it has a factor of 10 to low speed, the power requirement for those. Whether blowdown, it's in your hand. You can choose any power you want, because blowdown, you just fill in the tanks, the storage, and you run according to your capacity turnaround time. You can use any compressor you want. You just refilling will take time. So once your storage has the necessary settling pressure, you can run. The question is then how many runs you run per day, and this is according to your compressor. The more power you have, faster and shorter your turnaround time. Actually, I was building this one in our place, this blowdown. It was my project, and this one is the one in Lockheed Martin in Texas. Formerly it belonged to Vought. Vought is a company there were a lot of companies that were manufacturing airplanes in the US. I think there were 7 companies, and this is one of them that disappeared. I had opportunity to see the last aircraft came out from the assembly line of Vought. It was A7 it called, and that's it. And later on they were acquired by Lockheed. The wind tunnel there was acquired by Lockheed. It looks like a factory. You see to the left the storage tanks, cylinders, and from there is a channel, the main leg. These are the storage tanks, and here you see the main leg, and this is the tunnel and muffler and exit section, and here you see diffuser. Test section is here. Nozzle is here. Forgive me. Nozzle is here. Variable nozzle, and test section is here, and then diffuser. Second diffuser could be in supersonic. You have second diffuser. We'll discuss this. Tell me.
Blowdown.
Yes, blowdown, open circuit. Yeah, if it's blowdown, it has to be open circuit. Yeah. There were plenty of tunnels that were built like this. Ours is the same. NAL is the same, roughly. NAL is the same one. II the same, and there were tens of these tunnels that were built late 60s, and they are.
What is the meaning of double diffuser?
We'll discuss this later when we talk about compressible flow and the conditions to get high speed Mach number. Just to give you a hint, once you start the tunnel, the second throat, the second diffuser holds the shock wave away, so it won't blow back. One thing, and the other thing is you maintain low back pressure, so you can run with low total pressure. You want to run as low total pressure as you want. If you don't need special Reynolds number, you want to run the lower total pressure you can run to save power. So this one can hold it because it produces low back pressure. It helps you to maintain low back pressure.
How to evaluate the numbers?
Which one?
Enough.
We'll do. The what? The pressure?
Pressure.
We'll do that. We'll do that. What is the minimum total pressure, and how can you make it better? How can you improve the total pressure and so forth? We'll do that. It's nowadays it's in my compressible flow course, but it's something I'll give it here. Okay, so this is in draft. You have two systems. I mean, in draft, in this case, you have one system because it sucks the standard air conditions to vacuum. And there are wind tunnels that are connecting. Even one side is the storage, high pressure, and the other side is the vacuum. So the vacuum is giving you the back pressure, the advantage of this we'll cover. We'll go point by point. So the advantages of intermittent wind tunnel that are simpler and low cost. You need only single power to pump your storages, and during the pumping you can work on your models. Once it is there is turnaround till repumping, you can work on the model, change configuration, and you run again. And if there is a failure in a model, which shouldn't be, but if it happens, open loop is not suffering too much. It just go out. Usually it goes up, nobody's there, and everything fine. When it is in a closed loop, damage to the elements will be. And of course you have extra power, extra pressure to start the tunnel. I think we have to, when we have to break? I think another 10 minutes, it's okay. When you have a pressure, when you have pressure, when you have this, when it blows down, you have storage, high pressure storage. You can start in any pressure you like beyond the one you want until you reach to the limit of your storage pressure. So, for instance, in order to run Mach 1, your pressure ratio between the settling chamber and your test section or back pressure is what? 2, around 2. You need twice the back pressure in order to run Mach 1. But, so it means 2 atmospheres. 2 atmospheres, 30 psi's, that will be enough to start the tunnel. But you can run much higher pressure to start with. Because the storage like this will contain up to 40 atmospheres, maybe 600 psi or something like that. So you can run any higher pressure, and then with higher pressure you get higher Reynolds numbers. Once you are sucking like an in-draft, you are limited. You are limited to the atmospheric driving pressure. Total pressure is limited. You cannot play with this. We'll talk about this again. Flow conditions are more in control in the continuous, as we said also for the low speed. Checking.
I have one.
Tell me.
So in case of the pressure driven, no?
Yeah, blow down.
We'll have a pressure regulator.
Yes,
to
of course.
reduce the pressure, the storage pressure, say.
Yes.
Your settling chamber pressure to.
Yes,
we
yes,
can regulate
yes.
the complete
Right.
blowdown.
Right.
In case of in-draft vacuum,
Yes.
so how do we?
Also, you can regulate on the back pressure.
It's always that entry atmosphere. The test section is always at the.
Yeah, the driving is almost the same. You just regulate the back pressure. If you fully open, you are vacuum. You're running to
No,
vacuum.
your vacuum
You
will decrease, no? So
Yeah, but it changes.
velocity will.
So you have to regulate also the back pressure. You can regulate the back pressure. If you fully open, you get the full vacuum changes. If you close it according to back pressure to the vacuum and the storage, then you can regulate.
I have no idea about that.
The same as in the driving pressure. You regulate, right? You
Yeah.
can regulate also the vacuum. The same thing. Same way. Same way. So in continuous tunnels, conditions are more in control. Checking points, you can repeat your runs. You can go forward, back and forth. If it's continuous, you are not in a hurry to finish your sweep. You can make one sweep, another sweep, look around, and main sweep as you want because you are running in continuous mode.
Start-stop load will be higher in intermediate.
What?
The start-stop loads.
Yes.
It will be higher in intermediate.
It depends on you. Yeah, it depends. It depends. But what I wrote here, it's they are short. Once it starts, the shock wave passed the model, then it's only that's it. But in a continuous one, it builds up slow, the Mach number. So it will take time till the shock wave will pass the model. More time.
So the start loads will be higher in the intermediate tunnel.
It depends.
When the
It depends on the
shock-
pressure. Depends on the pressure.
Yeah, when it is passing, it will be it's a normal shock power.
Yeah, exactly. Starting and stopping loads are very harming, and you have to deal with it. I think I dedicate some time on that. I was writing to the STA some work on that. I was doing some work on this. Also, I have a patent. I have a patent on the reducing starting and stopping loads. I think I will elaborate on that a bit.
In continuous tunnel, flow conditions are more in control.
Yes,
What it,
you have time. You have time to settle your pressure, whatever you like. I mean, it's continuous. You build up your Mach number, and it's stable, and you can change conditions continuously
during
during blow, during the
the Mach number I cannot change.
pressure.
You can also change the nozzle. Usually this tunnel are variable nozzles. Yeah. And you can check points because you have stable conditions. And that's now the indraft over the blowdown. So indraft, when we are sucking from an atmosphere, you have constant pressure, as bad as it is, but it's constant. It's standard pressure. And less contamination, because when you come from compressor and storage tank, usually you have pebble beds and all kinds of stuff that will blow with the air. So when you suck from the free air, it'll be clean. Starting and stopping loads will be smaller because you're running with lower pressure usually. Vacuum is safer to handle than higher pressure. Higher pressure is always a danger, that high pressure with all will blow. Lower pressure is always safer. The noise is lower. To get air density, lower air density, naturally it's easier. Okay. Usually it costs less because vacuum pumps are usually cheaper. Less. A blowdown has advantages above indraft because you can control the Reynolds numbers. You can go up with pressure. Cost is significantly less. You can run very short runs. And you can make drop tests, simulating external stores drop, because your element will flow outside the tunnel. Nothing will happen. When it's in draft, your element fly into the vessels and it's wrong. Let's have a break, please. We'll have a break. We have a lot of time, and we are finishing the material. not working. It's on, it's on. This session will be a bit, I mean, it will be relatively shorter because we covered most of it, but you'll have plenty of time to ask and discuss. We'll cover, first of all, we'll finish with the last slide I've shown. Is the blowdown tunnel has disadvantages over the in-draft, that we are able to control the Reynolds numbers because we can run with higher pressure. The cost is less. Short time burning tests are possible. You can.
What is the meaning of burning here? Burning?
When you run, you burn you burn your pressure air. So you can. And drop tests are possible. As I said, when you are making some external stores drops, you just drop them and they blow out. Where in the vacuum, in the in-draft, it will come into the storage and you'll have to look for them. I don't know what you're doing there. So,
Reynolds numbers are widely available.
which?
Reynolds numbers are widely available.
Yes.
Is it because of higher pressure?
Yes.
consumption?
Yes.
No. What is the advantage? Is it in terms of density or in terms of
Density.
speed?
Density.
Density.
Density. Density. Speed is according to the nozzle.
Yes.
Nozzle. Nozzle determines the Mach number.
Okay.
Well, the pressure only has to be enough to start.
Right.
You must have the right ratio between the stagnation and the back pressure to run. But once you run, nozzle will determine your Mach number. We'll go over it a bit. I'm sure the youngsters are.
For conducting the drop test, the tunnel to be in vertical, is it required or it can be horizontal?
Horizontal. You have seen the VSSC wind tunnel. It's just like that. Have you visited this VSSC? No.
The drop test we have not.
Tell me.
The drop test we have not come across.
Talking about drop test.
What is done actually in drop test?
We'll cover that. I was wishing I can make for you for the HSTV, but both teams were too slow, and I'm afraid these days it'll jeopardize because of all kind of bureaucratic issues.
The dynamic model testing is different, I think, from drop test. Dynamic to get the dynamic derivatives.
Yeah, it's totally different. We'll discuss about drop tests thoroughly. It's part of the CTS and this issue. It's very important, I think, in high speed especially. Drop test is
Store separation.
store separation or phase separation.
That is just gravity drop. That is not
Jettison.
Jettison or the jettison is the other way. It's you are talking about jettisoning.
Yeah.
It's
When I say free drop or drop tests, you are talking about jettison, just release. Okay, now we'll talk about a little bit about hypersonic regime, which is beyond Mach 5. And again, we are talking about blowdown either in draft to vacuum or suction by or by ejectors. You must have very low back pressure for hypersonic because the pressure ratio between stagnation and back pressure is very high. And since you are limited in your driving pressure, you have to get low back pressure, very low back pressure. So either you drive it to vacuum or by ejectors. And the second type is the shock tunnels. Let's talk about wind tunnels that I was not designing, I was building. Actually, I got the material, the hardware I got from San Diego. They scrapped the wind tunnel, and I was pushing to build this wind tunnel some more than 30 years ago. I said, I see that US are taking out their wind tunnel, so we have to build our own. And as I spoke, they came out and said, okay, we want to develop this Aero interceptor missile. The Aero, you heard about the Aero? So I said, okay, I'll build for you the tunnel. And most of the work on that missile was work on that interceptor, Hertz Aero, was done in this wind tunnel, in our tunnel. Some of it was done for reliability, was done in ADC, but most of the work was done there. And since it was financed by the US Army, they were testing, and this number of officers from the Army, of the US Army, were sitting in the control room with laptops. And the moment the data came out from the wind tunnel, everybody was ticking and checking the results on the spot, see if everything goes well, and it was of course going well. And this is the way we're working. And so let's see how it looks. The tunnel, this is a blowdown tunnel. You see, you have two views. One is side view. The bottom one is side view, and the top one is top view. You don't see all the systems. You see only the system close to the tunnel. To the left, it starts from the valve. There is three pass valve here. Let me see what happens here. We don't see everything here. Wait, let me see. Yeah. See, tell me. Valve. This is the main valve. There is only one valve, and it is driven by the main compressor. We use here the driving of the compressor, which is 30 atmosphere or so. This pipe is coming from the heater. Such a wind tunnel is having lot of side systems. It has a heater, it has filters, it has dryer, whatever you need. I mean, you don't believe it. I was sitting in my office and I was looking outside one day and I saw the nozzles spread over the field, like, you know, and the nozzles spread over, and this part is over, and this, and I had one manager. He came from nowhere. He didn't have any clue what's going on. I told him, the guy, look, they're very tiny and very delicate nozzles. Why don't we collect them and put them somewhere so it won't, nothing happens to them? So then we put it inside, and I was starting to analyze what we have to do. And I was looking at the original tunnel. The original tunnel was a it was belonged to Lockheed Martin. Once they built the F-16, most of the experiments they were shifting to ADC, to the Air Force, because they were the main contractors. So all the modifications, everything that was done in ADC, they decided they don't need the the wind tunnel, all the complex. So they send all the complex over to us. The price of the wind tunnel, you never believe it, $1.5 million. Today, if you want to buy such one, it's 200. I think that's the price Boeing is quoting to you, 200 million. The building costed $8 million. That was the price of this wonderful wind tunnel. It's 4 feet square. I'm sorry, this is the hypersonic, but it came along with the supersonic, which is 4 feet. So along with all this package, we got this one that was spread in the field, and then when I started to see that we must have it, we collected and I started to see what elements are needed. I told my boss, I looked at the calibration figures, original ones of San Diego, and I saw kinks in the profile. It was not clean. So I was looking for the reasons why the profile, Mach number profile in the test section is not clean. So why is it not clean? Why it is not clean?
So nozzle is not correct.
Nozzle is okay. It was due to liquefaction. Due to liquefaction, once you have this contamination in your flow, your profile is disturbed. Now it can happen because it was hit not too much higher the limit. Any disturbance, any contamination will motivate the flow, the liquefaction. So I said to my boss, hey boss, you spend another 20,000 to buy dryer, you spend another 20,000 to buy filters, and we add it to the original one. And the profile after we mental this was really smooth and clean. I think I have photos. I have some plots of this later on. I have some of the profiles. So this pipe is coming from the heater. After dryer, filter, heater, it comes here. And when you start run the main flow through the heater, but the valve is sending the flow on the third board out to the muffler until temperature is stable. Once it's stable, the valve is open and the main flow goes through the mainstream. See, there are three pipes. One is in, one is out, and another is out. The one is the hot one. The out one is hot when it is not ready to run, and this is the regular. This is the running route. Now you need to fulfill two conditions. You see on the back here there is one ejector, and here there is another second ejector. These ejectors are sucking down the back pressure to a very low one, in order to get the required pressure ratio for any Mach number. Usually we were not saving air there. We just blew it maximum, and then the pressure was very low. Once the pressure is low, you make sure the temperature of the mainstream is right, and you blow it through the tunnel, and you get the right Mach number that you need.
It has got two ejectors, sir.
Yeah.
That is one,
And this is one.
The exit
Here.
that is another.
The exit is here. This is the backflare exit. Now, these days, this was the original construction. We just made it one way, no turns. This is another improvement. We made it only one way. It's going that way only. It doesn't come back. Here they save place. This is the muffler. This is the outflow. We turn this, and the outflow for us, it's here. It goes like this.
So this is an open type.
This is open, blow down.
And are there two test sections?
No,
Only one.
only one. This is the test section here. It's an open jet, and surrounded by vacuum cell, hermetically closed, and there is a injection mechanism. So once you start the tunnel, it is down. Once the Mach number is settled, you inject the model inside the flow, and you get.
What is that part? That long, I mean.
Which one?
Second is 7.83 meters.
Which one?
Top one.
This one?
Yes.
This is the outlet.
All right, but before that, there is a long, constant cross-section part is there.
This is ejector.
Oh.
Ejector. This is the structure of ejector. You can there is a standard way to design this kind of projector, and you get any pressure you design according to the mainstream and the circumferencing tube. You can find it anywhere. Tell me.
If it's a valve is there, I think. We are keeping some valve or something like that. It is looking like a model. That's what he's asking. The end of it, the ejector and
Here,
there.
nothing. It's
That is connected to some valve or something like that.
I don't know. This is the bypass of the hot.
Bypass, some
This is the
valve-
bypass of the hot
bypass valve is
of
there.
the mainstream.
Yeah, that looking like a
Yeah,
model.
this is the bypass of the mainstream, that you bypassing it until you get the right conditions, temperature and pressure. That's it.
Ejector, that is ejector air supply, no, sir, that one.
What happens?
For ejector to run, it requires air supply. So
Yeah, this is a different supply. Yeah, this is the supply of the ejector. Now the supply for the ejector is coming from the storage tanks of the supersonic
that
tower.
is cold air only.
Cold air. Yeah, sure. You want you prefer it cold because
And,
it
is
has
a
less
two-stage
more.
ejector system or only single stage ejector?
Two.
Two stages.
Yeah.
One is this one and
Yeah.
another one is,
There. This is the second one here.
and that is another ejector.
Yeah. So, tell me. We have originally we had three nozzles for Mach 8, 10, and 12, but they added with the time 5, 6. So they have also Mach 5 and Mach 6.
That high speed
Here,
is
cooling system is also incorporated on the nozzles.
No. Why do you need cooling system?
Because of the high temperature flow, you have to avoid liquefaction. You will be heating the system.
When it is cooling is there for the nozzle, for the nozzle, and sometimes you want to cool the model, but mostly the nozzle is cooled. Yeah.
Mach 8 and all. It
Yeah.
will be required to cool the
Yeah.
You have Mach 12, sir?
Yes, we didn't run it. I think we ran it once, but because we were limited in the pressure in the storage, we didn't run it.
So what is the T naught you have? T naught total temperature.
For this, I told you, it's enough. There's 750, something like 750.
750 K.
But I think I have a graph here for the liquefaction, and you can see. We'll look at it.
No. For Mach 12, we need around 1400 K.
No.
We have.
That's theoretical.
Okay.
That's
1400 K
theoretical.
At 100 bar. At 100 bar.
Okay, you look at the graph. I can't recollect.
Your II tunnel is only 750 K
Yes.
total temperature.
Yes.
So if you are running with a smaller pressure.
Then what is the P naught stagnation pressure?
30 bar.
You think I'm a technical note 11135? I'm not yet. I'm starting to learn. You know, my daughter, she remembers 35 numbers, figures behind the point for pi. I told her, stop it. You better invest your time in something more important. I don't waste my brain on that.
We have 750. We have in our tunnel we have 1400 Kelvin, but the P naught
Bless
is
you.
100
Bless
bar.
you. You'll have better margin. I'm sure you'll have more margin. You'll have more margin. But I can assure you that we didn't run ice there. We didn't run ice. We ran gas. You can see I think I have the HB the HB standard model photo, the Schlieren, you see it's very clean.
This heater is a pebble bed type, pebble bed heater.
Your heater is
The storage tank is with pebble bed. The heater is gas fired.
No, okay, pebble
Gas fired. No,
pebble beds.
why pebble beds? It's
gas-fired.
gas fired. You have two systems, the gas and the mainstream, and it goes through the heater. You have two different flow systems, so it's clean. So it
Mixing with the mainstream.
no,
Then it will disturb your
no, it's clean. The mainstream is going through the heater in a different piping. It's a heat exchanger.
heat exchanger.
Yeah. And if you see the photo, next one, this is a photo. I have one when I'm standing next to it there with more hair. I used to have more hair those days. So this is the this test chamber, and you see the window, and here is the model support. Yeah. This is from those years, those times, I think. So this is hypersonic blowdown. I can tell you stories about that if you want, but let's go on. VSSC. I found it in their brochure. I visited them because they bought ABCS, automatic balance calibration system. I was very impressed by the structure, by the facility. It was very nice. Very nice. One. So this is in draft. Let's talk some minutes about Carlspan. Carlspan hypersonic, not transonic. Carlspan are very known for their capabilities in shock tunnels and shock tubes. They were from the beginning working on this. I said regular wind tunnel is not capable of supplying all the conditions simultaneously. It cannot supply the energy, the temperature. So what you do is running a shock tunnel. We'll discuss the principle of shock tunnel, shock tubes later once. Generally speaking, it doesn't flow. The principle of shock tube and shock tunnel is that you're running a shock along your tube, and the flow behind the shock, actually, this is the flow over the model. The shock is running in the tube over your model, and you have a bulk of certain charged air, that this is the test. So the test may take 2 milliseconds, 3 milliseconds, 4 milliseconds. So in terms of data acquisition, I say there is no problem. These days, systems of data acquisition are very sophisticated. You can have any frequency you like. The problem is, and you ask yourself, if you put a model there, and you can calculate how many vortices or how many structures, fluid structures, can be created along the time it passes the model. Okay, so if there are only two phenomena that created on this bulk by this bulk, and you are measuring it, what type of measurement you get? I mean, if you have two occasions, let's say you have a separation from your wing on that tunnel, and during the separation there is one eddy and another eddy, and in 3 milliseconds you pick up only one eddy or 1.5 eddies. It's not enough to get an average feature of what's going on. So this is a questionable issue. But still, very good data coming from there, and I cannot compete with their experience. They are for tens of years in the matter, and they get good quality. high temperature, high enthalpy information. So actually, this was what I wanted to present you today. This is a rough overview of what we are doing. We covered type of wind tunnels that are available, not all of them, but most of them, and what type of tests we are doing, and type of low speed, high speed wind tunnels, and again, what type of experiments we are making there. Tomorrow, we'll dedicate the day mostly how we design a low speed wind tunnel, and we'll spend a lot of time on the measuring balances and calibration procedures. So after tomorrow, you'll be experts in low speed wind tunnels and calibration procedures, and you can make your decision if to buy or develop your own calibration system. But we'll keep that talk for tomorrow. I enjoyed the day. I hope you also enjoyed a bit. And if you have questions, let's talk about it. I mean, some of the questions may be interesting to others too. So if you have something in mind, please. I will try to. You are very quiet there. That area is very quiet. Why is it?
What is the principle of hypersonic wind tunnel? Actually, say for low speed wind tunnel, there is a fan, etc., and that way, I mean, wind is there. Similarly, for supersonic wind tunnels, high pressure storage is there. From there, it is coming.
Yes.
For hypersonic,
Same.
that same.
Same. Only thing is you add a heater.
Why you are heating? Is it for additional energy?
No, because somebody would like to heat to get closer enthalpy to real life. But the main objective here is to keep the air out from liquefaction, because once it expands to these high Mach numbers, static temperatures drops almost to zero, total zero. So it liquefies at 40K, I think, 40K or 50K. It starts liquefying. And to prevent that, you have to hit the stagnation. Yeah. Yeah, preheating the stagnation temperature, so it expands down to 80 or 90, not to 40, 50.
This II tunnel
Diameter is 45. The geometric size is 45 centimeters diameter. The true jet, because of mixing, is about 15 inches. It's 18 inches geometry and about 15 inches the true.
diameter is 15 inches.
Depends to what distance you have. 15 inches you can have it most of the test section. 14 inches you have all along, because there is the mixing layer.
For hypersonic tunnel, what is the shape of test section? Maybe circular one or rectangular one, right?
Because it's open jet, it would be circular. Because if it's squared, then it starts to mix and confuse. So you better start from axisymmetric. You better start from axisymmetric. I think most.
In case of closed system, like closed system, if you think of closed test section.
Yes.
What is the preferred shape
For what? For
test section?
for hypersonic? So what are you asking?
The shape for this test section, like is it required in a circular shape or square shape? Because ultimately it is connected with nozzle.
Yeah.
Nozzle
It can be closed. It can be closed. It can be closed. It can be closed and no, it can be squared.
Sir, S section, whether circular is better or two-dimensional is better. That's what his question.
Generally speaking, the squared is better. I mean, when the tunnels are small, it's better to handle it, because and also if you put a model, when you are squared or rectangular, then it's symmetric. According in all directions, it's symmetric to your model. When it is circular, then the distances are varying. So in small wind tunnels, when you are close to the walls, you better have a square or rectangular.
This is for supersonic?
Also small, low speed. If you want to have big models, and you start getting closer to your walls, you better have straight walls, because rounded walls will be complicated your calculations of correcting and also on everything. It's a good question. I mentioned it somewhere, but I missed it. It's good.
How do you select the length of the nozzle?
We'll tomorrow design. You'll know. I assure you, if you come and you will not sleep, you'll know. Not personally, I'm talking generally. I hope I'll be awake to talk about it.
For measuring hinge moments in the wind tunnel.
Hinge moment? Yes.
What are the precautions we have to take and how we can plan the test?
I was not covering this matter in the balance issue, but what exactly are you aiming at? I'm not sure what you're expecting to.
What are the parameters we have to take? I mean, what are the few tests so that we can optimize the number of tests and we can get the better results. In the sense,
You're talking about hinge moments?
in
Usually, traditionally, hinge moments, you just design your own balance for that, because everybody has his own scale and requirements, so you better, and configuration. As generic as you like to do it, so it'll be a kit that can be installed for any configuration. At the end of the day, you design your own balances, and usually they mustn't be 6 components. They can be only less. They can be 3 components or 4 components or whatever you're looking for. The mainly pitch, normal, axial, side, not so much. Maybe rolling moment you need. So you design your own. And then you fix it. You have some arrangement to manually fix the predetermined angles for the fins, to test it in different angles. Actually, I hope this year one of my teams in 4th year, they'll have a project with one of our customers in the country, one of the defense guys, that wants to build a kit, automatic kit, that it will change the angles during the test, because they are paying a lot for each blowdown. Each blowdown is cost. In one blowdown you can have several angles, because it's a waste. At the moment, let's say transonic you can run. Let's say you can run 40 seconds continuously. If you run 30 seconds, you don't pay less. The wind tunnel guys will gain from it, because they'll have to repump less time. But you don't gain. You pay for pull-out. But now come and ask, I want to run 40 seconds, and during this run, you make 2 sweeps. You change the angle, or 3 sweeps, depends on how long is your run. So you can double your production. So this is something, for sure it is good for continuous tunnel, that you don't have to restart and the tunnel, and because continuous tunnel is time consuming to restart it, to run it. It takes time until it's stabilized and stores. So if you already stabilized in the Mach number that you want to run, you better automate your model, so you can change angles of fins and so forth. Whatever you can change without stopping the tunnel.
correct the base pressure?
You just measure. You just measure.
Sting will be there. Sting will be having.
Yeah, yeah. You just mount tubes and you measure the base pressure, and you calculate. You correct it. You correct for it, because when you have this, if it's a jet engine, you don't have that pressure, so you have to correct it to clean it from your drag. So you just measure that. You have
Not fit out or anything.
two tubes, two total tubes there. That's all. And it sits inside, so it measures actually the static pressure.
Sir, in case of external balance, in case of external balance measurement,
In case of,
external balance,
yes,
how balance is sensing the modal force or moment?
we'll talk about tomorrow. We'll talk about it thoroughly. We'll cover this. These questions I was not aiming to.
This sting diameter, any criteria is there?
Yeah, you mean
What's the
With respect to
diameter and
model,
length of the
what
sting?
should it sense?
usually you are limited. You are limited according to the space. You need space that once the balance bends, you don't touch. So you calculate how much. That's all. Deflections. You see that.
There will be some back pressure zone will be there. That's sufficient to interact at some wave formation or something.
There will be always back pressure, and you have to eliminate it by calculations. Yeah. Yes.
So this blowdown test, it's very expensive.
Yes.
And that too for a short time. But still, they are developing more and more tunnels nowadays for this blowdown testing.
Yeah, because it's cheaper. The same wind tunnel, the same nozzle that I was mentioning it, the same nozzle, if you want continuous, the power for the fan will be, it depends on the compressor you like to have, but I take hours. Hours is, I'm not sure about the figure. I think it's 1 megawatt. Megawatt, whatever we are under for the supersonic. I think it's the same at NAL. If you want it continuous, it would have been 4 times more, 4, 5 times, 8 times more. The power consumption.
But what exactly the flow features that you are getting by having this blowdown test in
What-
addition to this conventional method?
The advantage of blowdown is that it's less cost. It's less cost, much less. Not only the construction, also the operation. Once your operation requires a local electricity company, you will be limited by the Ministry of Energy or the municipality. They'll tell you you can run only third shift now because you are sucking most of the energy from town. That's just real stories. That's real stories. Even the blowdown, when I went to Dallas, I was attending some testing there several times. They were running third shift. They didn't let them to run during the day because it was consuming too much power. So imagine if you put their fan, a continuous one, you will never able to run. So this is the main issue. And also, it's less complicated. I mean, construction is cheaper. Systems are less complicated, and it's very. I mean, you can build it anywhere. I think blowdown, it's a very cheap instrument. You can build it even in the university. You just have the pressure, you just have the nozzle, and you can show them any Mach number that you would like to show. Very fast. Take a MATLAB solution for characteristic nozzle, and you can get the coordinates, and you have a nozzle, and you make it, and easy today to design.
Will you be talking about various corrections, MCJ corrections,
Which corrections?
mass cavity and jet correction, typically what they do after test is done?
In case of a flow-through model, the flow-through corrections.
I am not covering this. I was not covering it. I think we are losing some of our audience already, right? though they are interested, we are losing them already. I think if there's something specifically I can contribute, I will talk. But I think
Basically to understand how MCJ correction is done.
mm,
in order to just understand.
I'm not sure. I know. I was not doing too much work with flow through, but we can think
It's not
about.
only for flow through, even otherwise.
Let's talk about it. Let's talk about it. I hope I'll be able to brainstorming with you about it. I'm not sure I'm experienced on that. Yeah. Even I don't know anything. Yeah, I don't intend to, but I really lucky. I'm really lucky. I could interact with all these guys on all different types of technical issues, and it's really good. Okay, so we'll have a break till tomorrow, and think of good questions tomorrow. We'll answer if we don't still need something. Tell me. Yes, we'll design.